All right, moving on to part two, the first lecture. We're going to talk some more in depth about strongly coupled models of new physics. As I said, this will be mostly composite Higgs and composite dark matter. I'm going to make some general remarks first. So I gave a lot of motivation in the previous part, but you might ask why, a lot of these models just sort of look like, particle X but composite. And you might wonder why that's interesting at all. Like, this is a problem which is well suited to lattice. I've tried to motivate that, but are we just looking for problems that we know how to solve here? We have a hammer. Are we looking for nails? And the answer is partly. I mean, we do have a hammer. We are looking for nails. But there are some better reasons to be interested in composite theories, so reasons why non-lattice people are interested in them. And in fact, compositeness, of course, has a really rich history in physics. There are many objects that we initially thought were fundamental that turned out to break into smaller pieces, right? Famous experiments by Rutherford and by Thomson broke us down from atoms to electrons and nuclei to electrons and protons and neutrons, and eventually we got to QCD. So we have a long history of things that we thought were fundamental actually being composite. And, the standard model is a set of fundamental particles, but by fundamental, we really just mean that down to these smallest distance scales that we've probed so far, we know that they're fundamental. We know they don't have any substructure. But that's only true so far, right? So that's anything in the standard model could easily have some substructure, could be composite at some scale we haven't probed yet. And so that's kind of the additional broad motivation. We've seen compositeness before. We could easily see it again, certainly allowed by observation. And by the way, we're going to be focused on compositeness involving gauge theories. That's going to be the main thing that we care about just because of the context of these lectures. But of course, compositeness doesn't have to mean gauge theory. You can ask your local string theorist about string theory, which of course, if string theory is true, then everything is composite. Everything is just made of strings. So just to say compositeness, gauge theory is not the only thing that can give us compositeness. Okay, so let's start with composite Higgs. The Higgs boson is a very important part of the standard model, and it's kind of a special particle in that it's the only fundamental scalar that we have ever observed in nature. None of the other fundamental particles we know about are scalars. And scalars, unfortunately, have some theoretical properties that are kind of uncomfortable. Again, this is referring to the Higgs naturalness problem. They tend to be subject to large quantum corrections. And so this is one of those reasons, that one of those motivations for extending the standard model. And we could ask the question, well, what if the Higgs is actually not a fundamental scalar? What if instead, like all the scalars that come out of QCD, it's actually a composite bound state of something else? So for this to be true, there has to be a new strong sector somewhere up at the electroweak scale. And that strong sector has to be involved in electroweak symmetry breaking and in generation of the standard model fermion mass, right? The Higgs does both of those things for us. So if we replace it with some new strong dynamics, then the strong sector has to do both of those for us. And this is kind of a nice idea, not just in terms of sort of fixing the issues with having no fundamental scalars around, but also because, from an experimental point of view, there's sort of a rich set of interesting things to look for if this is true. For example, if the electroweak bosons have some composite component to them, you'd expect to see excited states, radial excitations of those things. So you can look for W primes and Z primes and things like that. If the strong interactions are responsible for fermion mass, that should be something. There should be some significant deviations you see in the properties of fermions. Especially in the top quark. The top quark, of course, couples most strongly to the Higgs field. So you expect to see something unusual in top physics, or deviations from sort of perturbative predictions there. Okay, so there's all kinds of interesting sort of experimental consequences of this, but let's come back to the basic idea first. And we're talking about replacing the Higgs mechanism. So I'm going to start by just reminding you very, very briefly how the Higgs mechanism works in the standard model. And the slide is about 2 ways to break electroweak symmetry. So first is Higgs. So for the Higgs mechanism, we have our symmetry breaking Lagrangian. involving the Higgs doublet, capital H. So we have a kinetic term, and then we have some potential. Say mu squared h squared minus lambda h to the 4. And the parameters of the potential are chosen such that the Higgs gets a vacuum expectation value, V. Okay. And we can re-expand around the minimum, around the vacuum expectation value. So we can rewrite the Higgs field as capital H becomes V plus little h of x. And then we can rewrite the Lagrangian. So there's interactions buried in this covariant derivative here with all the gauge bosons, SU2 left and the U1 hypercharge. And if you go through the exercise of expanding this out, what you'll find is that you get a kinetic term for this little h field. And then we get 1 plus h over v squared times, go to the next line here, mw squared w mu plus w mu minus plus 1/2 mz squared z mu squared. Okay, and there's predictions. So I've skipped over a bunch of algebra here. Part of this is that the MW that you see here, of course, the only things it can depend on are electroweak couplings, which are buried in here, and V. And one of the predictions of this, the Higgs model, is that MW is GV over 2, and that MW squared over MZ squared. Do this on a new line just so I don't run out of space. So the ratio MW squared over MZ squared is a prediction of this. Cosine squared theta W is given by G squared over G squared plus G prime squared. So those are the SU2 and U1 couplings. Okay. And this parameter here that's given in terms of the couplings, that's the Weinberg angle, just to remind you. So of course, these are very concrete predictions for what the W and Z masses are. We also have very concrete predictions about how this little h field, which is the Higgs boson that we've observed, interacts with W and Z, right? The interactions end up being proportional to their masses. Okay, and all this just falls out of this symmetry breaking argument where we observe that this potential gives a vacuum expectation value and then we re-expand. Okay, and this should be review on some level. But I promised you 2 ways to break electroweak symmetry. My second way, actually, is from QCD. Okay. Let's see how this works. So the symmetry breaking Lagrangian, in this case, I'm just going to take the leading order chiral Lagrangian. So I have f pi squared over 4, trace of d mu u dagger, d mu u. Okay, and here u is the usual nonlinear function of the pion fields, e to the 2i over f pi, sigma a pi a. Okay, so the sigma a are the Pauli matrices. So this is just simple SU2 chiral perturbation theory, which you will see elsewhere in this school if you haven't already. I may not be matching the conventions of the other lecturers who've referred to this. I'm more interested in the qualitative results here, so don't worry too much if my conventions are off by 2 or something. Okay. Now, onto the symmetry breaking part of this. So the form of this LSB follows from the fact that the QCD chiral condensate is not equal to 0. Okay, so that's, again, just like the Higgs case, we have a vacuum expectation value. In this case, it's of the quarks themselves, or this quark bilinear. And now I can take LSB, the chiral Lagrangian, and by the way, I'm coupling it to electroweak here, right? So I have these covariant derivatives. Once again, that's where the electroweak fields live. And I can expand, and what do I get? So I find MW squared, W mu plus, W mu minus, plus 1/2 MZ squared, Z mu squared, plus order pi cubed. So I should stress, this is a nonlinear Lagrangian in the pion fields. There's an infinite number of terms. I'm just working at leading order, so I only keep terms up to order pi squared, just the kinetic terms essentially. And you'll notice that I ended up with mass terms for the W and Z again, and in particular, I have predictions. MW is equal to GF pi over 2, and MW squared over MZ squared from QCD is exactly cosine squared theta W. Okay. Exactly the same predictions. So we don't need the Higgs mechanism. QCD breaks electroweak symmetry for us. That's all we need. Okay, so obviously we still need the Higgs mechanism. That's not entirely true. So there are two problems with this. One problem is that we know what F pi is. F pi, depending on your conventions, is about 93 MeV, which is much, much less than V, which is about 250 GeV. Okay, so in other words, if we relied on QCD to break electroweak symmetry, the W and the Z bosons would be sitting down around the 1/100s of MeV scale. Observationally, they are not. And the second issue is that part of what I didn't mention over here on the left is that this field H is a electroweak doublet. It's a complex scalar field, so it has 4 components. In fact, the 4 components of H become, 3 of them become the longitudinal components of the W and Z bosons, and this little h that we're left over with is the Higgs boson. Okay, so in other words, this mechanism where we give mass to the electroweak gauge bosons, of course, a massive gauge boson has 1 more degree of freedom than a massless one. Longitudinal degrees of freedom have to come from somewhere. They come from the Higgs doublet in this case. On the right, the same thing has to happen, and we find that the pi plus and minus and the pi 0 must be becoming the longitudinal modes of the W and the Z. And there's nothing left over. So the fact that we see in nature pions that are not longitudinal modes of the W and the Z means that this is, or rather, if QCD was solely responsible for electroweak symmetry breaking, we would not see pions. We would only see W and Z bosons, and their longitudinal modes would be the pions. Okay. So the story on the right doesn't work, but it's really nice. It's kind of compelling, right? That the standard model already has electroweak symmetry breaking into it. We don't need to add a Higgs field to it. And this suggests that what we can do is we can scale up, take F pi to V. And of course, we can't replace QCD. We need that where it is, but we take a new strong interaction. We put it at the electroweak scale, and then we can have this electroweak symmetry breaking follow exactly as it does in QCD. Just the formation of some condensate breaks it instead of needing a Higgs boson. Okay, this is sort of the creation myth of composite Higgs. This is the original sort of story behind the idea behind how this strong dynamics at the electroweak scale would work. And this went by the name of Technicolor, this sort of model. I'll write it up here. Okay. And you might think to yourself, there's an obvious problem with this, of course, which is that it doesn't produce a Higgs boson, and we've seen a Higgs boson, and you're right. Let me come back to that point, though, because I want to finish the creation myth first. So as I said, the Higgs does 2 important things for us in the standard model. It breaks electroweak symmetry, but it also produces fermion masses. And we have to worry about that too. Okay, so once again, we have a story of 2 models. In the Higgs case, we know how this goes. The mass of fermions comes from Yukawa coupling. So I have, for fermion F, something like YF, F bar right, Higgs doublet, F left, plus Hermitian conjugate. These are both doublets. All the charges work out, so these are neutral operators. And the Higgs takes on its VEV. We plug in the VEV here and we get YFV times F bar F. Yeah. So this term in brackets is the mass of the fermion. Comes from the Higgs VEV. So what about Technicolor? How does this work? Well, so if we think about it for a moment, we have to have, so suppose we have some, we'll call them Techni fermions, psi, and psi bar psi not equal to 0 is the thing that broke electroweak symmetry for us. Okay, so these are the new particles we have to play with. And now we have to make something that looks like a mass term using these new fermions. So the obvious way to do that is to write down a 4 fermion interaction. Okay, so the mass Lagrangian in the Technicolor case looks like some coupling over lambda squared, psi bar psi, f bar f. Okay, so this is dimension 6, so that's why I have a 1 over some scale squared here. Yeah, and now it sort of works the same way as in the Higgs mechanism, whereas in the first case, I know that I have this condensate of the fermions, psi bar psi is not equal to 0. And that means I can sort of plug in the vacuum expectation value here, and I get GF expectation value of psi bar psi over lambda squared f bar f. Okay, so it's still a fermion mass term. Still generated by the same vacuum expectation value that gives me electroweak symmetry. So I can hope to get sort of the same structure that I do from the Higgs. Okay. This is the basic idea. Now there's a couple of problems that occur immediately here. Okay, so the first problem, I'll just finish on this slide. We have 3 generations. And this means you sort of need to impose some extra structure here, right? You know, in the Higgs case, we can just have the Yukawa couplings have some generational structure to them. We could do the same thing with this coupling G here. But that's effectively the same thing as saying that we're going to have some extra structure in these cutoffs. So we have 3 generational cutoffs, say lambda 1, lambda 2, lambda 3. And it's going to require us to have sort of 3 different scales living at high energies where these sorts of operators are generated for us for the 3 different generations. So it's a lot of extra structure, but not necessarily a problem so far. This makes the theory complicated. I said this was the messy part. The second problem is a much bigger problem. And the second problem is I have this 4 fermion operator, psi bar psi, f bar f. And whatever physics that creates that, wherever it comes from, there's no symmetry at low energies that obviously forbids me from having the other combinations of those fermions. So I'll call this other 4 Fermi operators, right? So our Lagrangian looks like it also contains the following. I'll call this G4 over lambda squared psi bar psi plus G F C and C over lambda squared F bar F bar F. Remember, F were the standard model fermions. I've labeled this FCNC. This is a flavor changing neutral current operator, right? If I take 2 different sets of standard model fermions here, this will allow me to change flavors. And these are really tightly constrained by experiment. Okay. So for example, KK bar mixing gives the constraint, if I say GFCNC is order 1, lambda has to be greater than about 10 peta electron volts, 10,000 GeV. Sorry, I think 10,000 TeV. Yeah, it's a very high scale. And this forces MS and MC to be too small, basically. Right, because remember, whatever this scale lambda is here, it's the same scale that shows up in the operator we want to give us fermion mass and the one we don't want to give us this flavor changing neutral current effect. Okay. Now, you can try to do model building. You can try to build a model with some symmetries at high energy, such that just this coupling, just the FC&C coupling is much smaller than 1, for example, and keeping lambda fixed. This is such a really strong constraint that it's very, very difficult to do this. So there have been efforts in the literature, but it's extremely difficult to build the model to accommodate everything with a single scale that's generating all these operators for you. There's one other way out of this. Okay. And it requires us to think about sort of the Fineman diagrams that are responsible for these two things. So I have this diagram that gives me, say, flavor changing neutral currents of d bar s, s bar d, right? My 4 Fermi operator sitting in the middle here. And I want to compare that to the operator that gives me the strange quark mass. And that's going to be s bar s with psi bar psi, but the psi bar psi I want to be closed into a loop. Okay. I just want a mass operator. So the only external state is S. And where there's a loop integration. Okay. And what the loop integral does is it enhances the strange mass by a factor which is roughly eta, which is the exponential of the following, the integral sort of from the low scale to the high scale. So roughly, very roughly, electroweak scale up to lambda of d mu over mu, gamma of mu. Gamma of mu is the this is the psi bar psi anomalous dimension. Okay. And I'll say more about anomalous dimensions later in this lecture series. For now, just suffice it to say that this is sort of the thing that captures. What's important here is that this is a loop, and we do a loop integral over all these scales. And this function, the anomalous dimension, captures what's happening inside the loop at all those scales. And this is something which you have to determine non-perturbatively, because this is, these are strongly coupled. So there's glue being exchanged in the middle of this loop and so on. Okay. And this enhancement can be large if we have gamma mu approximately 1. And again, I'll say more about anomalous dimensions later. There are bounds that say it can't be much larger than 1 in general. And 1 is sufficient to relax a lot of these constraints and let you have mass generation without running into these flavor changing neutral current problems too badly. But it's not just something that's approximately 1. This is approximately 1 over this entire range of scales from V to lambda. Okay. So pictorially, you want something where if this is gamma versus mu, it should be monotonic. So I'll try to write a little more monotonically. Mu versus gamma. Here's 1, and you want to sort of be plateauing for a long range from between these two scales. Okay. And part of the reason I'm going through all this detail is this sketch, this idea motivates a lot of what people try to look for in the field theories that they're trying to match onto composite Higgs, right? If you know what these anomalous dimension operators do in QCD, they look nothing like this, right? It's sort of a monotonically increasing function towards low energies, but there's no sense in which you're going to get it to plateau at a large value over a long range of scales. And this sort of necessary feature, this forces us to go looking for theories that are definitely not QCD, that behave very differently from QCD. Okay. All right. This is one of the things we're looking for. All right, so that's the end of the creation myth of Technicolor, and now let me come back to the more modern point of view. So as I said, Technicolor, the original formulation is you sort of are just breaking electroweak symmetry with this condensate. You create pions, they get eaten by the W and Z. That means you don't need a Higgs boson. So Technicolor is a Higgsless theory. This is obviously bad based on what we know now from the LHC. It was a lot more appealing before the LHC discovered the Higgs, but now we know we have a Higgs boson, and we know that its interactions are in fact pretty standard model Higgs-like. So here's a summary plot from the Atlas experiment. Without going into too much detail, these kappas are roughly, there are factors that modify the Higgs couplings to each of these sort of particles named, so Z, W, T, B, and so on. And you can see everything is pretty much consistent with one, with fairly tight errors. Okay, so we know now there's a Higgs. We know it's pretty standard model-like. And what this requires, in a nutshell, between these two between this plot and the fact that there is a Higgs, is that we must have F much larger than V. Remember that Technicolor had the feature that the electroweak symmetry breaking scale V was exactly just F, so the pion decay constant. Or you can think of it as some scale, the scale of the compositeness, the scale of the strong dynamics in some sense. And now the fact that nothing has been observed very close to the electroweak scale by the LHC, and the fact that these couplings are so standard model-like, F must actually be much larger than V. Yeah. This is so-called little hierarchy between the electroweak scale and whatever the scale of new physics is in these composite Higgs models. Okay. So how do we fix this? There's sort of an accepted way to do this, and there's a more speculative way, and I'll mention the speculative one first. Is that you may try to, maybe you can try to construct a theory that where the condensate does all the breaking for you. It's a Technicolor-like theory. You don't need a Higgs boson, but something that looks like a Higgs boson shows up anyway. This would be something called a dilaton or a pseudodilaton. And this is kind of an interesting possibility. If you see, for example, this paper, which is not by Lattice authors, 7081463, they point out that there's a lot of similarities between a Higgs and just a generic dilaton. A dilaton is something that is a Goldstone boson of scale invariance, basically scale symmetry breaking. And one of the consequences is that it couples proportional to mass, which is exactly what the Higgs boson does. So it can be difficult to distinguish these. I will say that there's a significant model building challenge here. This is very speculative. Basically, it's hard to keep the Higgs mass much smaller than F. And we have to have that because of the experimental situation. Okay. So interesting. There's interesting connections to Lattice, which I'll hopefully say something about later. But I want to move on to the other approach here, which is called Pngb Higgs. This sometimes goes by the name, people will just sometimes say composite Higgs. This is what they mean. And the idea here is that instead of making the condensate break the electroweak symmetry for us, we preserve it, okay? And the reason is that this condensate psi bar psi not equal to 0 in Technicolor theory, if you think about the chirality of the fermions going into this, we have a left-handed, a right-handed fermion, psi left and psi right. This breaks electroweak symmetry if we do what we do in the standard model and we give this one SU2 left charge and this one has nothing. Then the existence of this condensate breaks the symmetry. But we don't have to do that. We can assign psi left and psi right to both be in the box representation, the fundamental of SU2 left. And if we do that, this condensate doesn't break symmetry at all. So those are the two sort of extreme cases. So in the Technicolor case, we assign the charges so that this sort of maximally breaks electroweak symmetry. If we do this, we put them in what's called a vector-like representation of SU2 left, then the condensate doesn't break electroweak symmetry at all. Okay, and it turns out the second thing is a good starting point for the Pngb Higgs construction. And what we do now is we construct the chiral symmetry G, and this breaks spontaneously to G over G mod H. Okay. And we're going to insist that H contains the electroweak symmetry group. So the unbroken, we construct things in such a way that this condensate doesn't break electroweak symmetry at all. And what you can think of here, what's happening sort of qualitatively, is that the strong dynamics is generating a particle that looks like a Higgs doublet. So it generates an H, and we get a V of H. We get a potential. The potential comes from loops, electroweak interactions. Without getting into too much detail, basically, this is a theory that at first order doesn't break electroweak symmetry at all, but it produces a Higgs boson for us. So this is much more, this is more what you might have guessed when I said composite Higgs to begin with. And a consequence of this is that we predict from this model that V is not just F, V is equal to F sine theta. Theta is called the vacuum alignment angle. And it comes from sort of balancing what these loops, what the contributions to this Higgs potential look like. Okay, so I can't go further into detail on that without getting too far into the weeds. But I'll just observe that this construction lets you then satisfy the experimental constraint, have a V over F, which is much smaller than 1. And that produces a Higgs, which is composite, but nevertheless looks very standard model-like at low energy. So this can be compatible with experimental results so far. And as we'll discuss later, if you want to embed this whole symmetry group into the chiral symmetry breaking, you can't do it with a theory that looks like QCD. Once again, you find that you need a larger chiral symmetry group than QCD. So the original Technicolor story relied on an exact copy of QCD. You just needed SU3 and 2 flavors of these technifermions, and that's it. This is once again a reason that we have to go beyond QCD to some other exotic strongly coupled theory to have a symmetry group large enough to even accommodate this. And there's additional constraints I didn't get into here that motivate sort of a certain subset of all of the possible strongly coupled theories you could consider. Okay, so that's all I have to say on composite Higgs. Let me move on next to composite dark matter.